In this video, we're going to talk about a second form of spectroscopy called nuclear magnetic resonance, or NMR spectroscopy, that's going to allow us to go from just having a molecular formula of the molecule to being able to identify the entire structure of the molecule. And it's something that as organic chemists we use every single day in the laboratory. So this is contrasting to the IR spectroscopy that we talked about in the last video because, as you remember, IR spectroscopy only allows us to identify functional groups, whereas NMR is going to allow us to identify the entire molecule. And so the way that NMR works is that you're using magnetism to interact with nuclei that have odd numbers of protons that are isotopes. So for example, a list of nuclei that can be seen in the NMR are shown here. So protons, which is the most useful, carbon-13s, which happen about 1% of all carbons, which are normally carbon-12, are carbon-13, so we can see those. We can see nitrogen-15s, fluorine-19s, and then phosphorus-31s. The way that NMR works is that when you have these isotopes, that they're basically like mini magnets, right? So if you have an odd number of protons, for example, you're going to have a little magnet. And so each of these magnets, when they're just in free solution, which is shown here on the left, they're kind of all pointing different directions. So what we do with NMR is we basically use a really large magnet to orient all the magnets in the same way. So we apply a magnetic field that we're going to indicate as B0, and we're going to apply a magnetic field which is going to basically excite all of the all of the isotopes to be oriented so that they are opposite what we call the beta spin of the NMR, or of the magnetic field that we apply, right? Because you can imagine with magnets, like the North Pole goes to the South Pole and vice versa. So when we apply a big magnet to all these little magnets, they all flip over so that they're opposite of the magnet direction. And then what we actually measure in the NMR is the relaxation from the beta spin to the alpha spin state when the magnets flip over when we remove the magnetic field. So anything that's a magnet can be read, or any atom that has magnetism can be read on an NMR. So there's going to be four things that we need to learn from our NMR spectra that we're going to see at the end that will allow us to identify what the structure of our molecules are. And that's going to have to be with the location of the signals on the spectra, the number of signals on the spectra, how big the signals are on the spectra, and then what we call splitting, or how many peaks each signal has on the spectra. And so we're going to walk through these one by one in this video. So the first one that we'll talk about is the location of the signals in the spectra. So what they do is they show how shielded or de-shielded a proton is. And what those terms mean are whether or not a proton, and so we're looking at hydrogens here, whether or not a proton is near something that is electron rich or electron poor. And that's what we're talking about with shielded and de-shielded. So for example, if we have this compound here, we have hydrogens that are coming off of the carbon, and carbon is less electronegative than oxygen. So carbon is more, there's more electron density being shared between the carbon and hydrogen. So we call those shielded, right? Because the electron density is shared evenly between the carbon and hydrogen. Whereas with the oxygen is electronegative, so we have a dipole moment shown in pink that is pulling electron density away from the hydrogen towards the oxygen. So the hydrogen that's attached to the oxygen is less shielded or de-shielded. So then we get the term shielded when there's more electron density around the hydrogens, or de-shielded when there's a less electron density around the hydrogens. And based on the shielding, our peaks are going to show up on different locations of the NMR spectra. So for example, here's what an NMR spectra looks like. It's going to be magnetic field on the bottom, and we'll talk about the x-axis in a minute. There is no y-axis. And then we're going to have peaks as we move from a high magnetic field on the right, which we call upfield, to the low magnetic field on the left, which we call downfield. And so the low magnetic field are going to interact with things that are de-shielded, right? Because if you imagine there's less electron density, it takes less energy or less magnetism to interact with them. So here, the peak that is representing the hydrogen that's on the oxygen is more downfield, or interacting at the low magnetic field because it's de-shielded, whereas the hydrogens shown in blue that are on the carbons are more shielded, so they're interacting in a higher magnetic field, or upfield. And so the location of where the points go on the graph, or where the signals are on the graph, are going to tell us what kind of electronic environment are happening around the hydrogens. So in order to be able to make it so that if you take an NMR here at UNC Asheville, or if you take an NMR at some other institution or some other lab, that they all have the same reference, we use an internal reference called tetramethylsilane, or TMS, that we set to be 0 on our x-axis. So you'll see this in a minute. And so trimethylsilane structure is shown here. And we kind of set that to be our 0 point so that whenever you compare NMRs, you can see, can compare them across labs and things like that, and everybody's reference point is the same. So if you see a peak at 0, and the NMR will do this automatically, it is this trimethylsilane that's in all of your samples. And so an example of location of protons and their shift, their chemical shift compared to an electronegative atom, is shown here. So if we compare butane, that has all just carbons and hydrogens, all of those hydrogens are kind of going to show up around the same chemical shift, so around 1, because they're pretty shielded, so it's pretty far to the right, because it's just carbons and hydrogens. And they're all very similar carbons and hydrogens, so they all show up about the same place. But if we change butane and replace one of the hydrogens with a bromo on the one carbon, as shown on the molecule on the right, you can see that now the hydrogens that are on the alpha carbon that are closest to bromine are much more shifted downfield. So they have a higher ppm. So they're at 3.4 ppm, whereas the hydrogens that are on the farthest carbon away from the bromine, the delta carbon at the end, they're at 0.9 ppm. So as you move away from the electronegative atom, the thing that's removing electron density and de-shielding, you go lower and lower in ppm, more upfield, which I'll explain in a minute. Okay, so you do see effects across the molecule, but they diminish over space in terms of shielding. So you can also have special shielding effects from aromatic rings, or benzene in this case. So remember, when you have a ring that has conjugated double bonds, so double bonds on every other carbon group that are conjugated within the ring, they make their own special magnetic field. And I won't go into much detail about this, but the thing that I want you to remember, which is highlighted in blue, is that when you have hydrogens that are on an aromatic ring like benzene, they're going to show up between 7 and 8 ppm on the chemical shift, because the conjugation and the resonance within that ring helps de-shield the hydrogen, so they move downfield. Okay, so the take home for location is the more shielded, or the more electron rich the hydrogens are, the higher upfield or to the right on the spectrum. And whereas the more electron poor or de-shielded the protons are, the more downfield or to the left on the spectrum. And so the next thing that we learn from the NMR, after we learn about the location telling us about shielding, is going to be the numbers of signals. And so the number of signals is going to show how many different kinds of protons are present. So some protons in the molecule are going to be identical to one another, so they're all going to show up in one signal. So we're basically looking for unique protons in this way. So, for example, if we take this molecule here that has 4 different CH3 groups, right? So it has the 3 circled in pink and the 1 circled in green. What we see is that if we take an NMR, so now to show you the axes that you're looking at, you see that the x-axis in the ppm from 0, which is our TMS, our reference point, all the way up showing to 10. We see that we have 2 signals in the NMR, 2 peaks that are highlighted. And the reason we only have 2 peaks, even though we have, 12 different hydrogens, is because all of the hydrogens that come off of a single carbon are identical. So for example, all the hydrogens coming off the green carbon are the same. So they all show up in one signal. And then those hydrogens are unique, or different from the other CH3 groups that are highlighted in pink, because they're closer to the oxygen, whereas the other CH3 groups that are highlighted in pink are 1 carbon away from the oxygen, right? So that the green hydrogens are closer to the oxygen, they're more de-shielded, so they're farther downfield, showing up about 3.2, whereas the hydrogens that are in the pink, they're all identical to one another, because if you think about symmetry, they're all seeing the same environment. They all see that carbon that they're attached to. But because they're attached to the carbon, they're more shielded. So they're upfield at around 1.3. So when you're looking at number of signals, that tells you how many unique hydrogens that you have is the number of signals. So in this molecule, we have 2 sets of unique hydrogens. We have the ones on the CH3 group in green that are right next to the oxygen. And then we have the 3 sets of 3 that are in pink that are attached to that central carbon. Here's another example showing you how many unique hydrogens that we have. So here in this molecule, we have 3 sets of unique hydrogens labeled A, B, and C. And so A are all the same as one another because, again, they all see the same carbon environment. And then C, the hydrogens C are all the same, are both the same because they're attached to the same atom. And then finally, hydrogens B are the same because, again, they're all attached to the same atom and they see a different environment than the H methyl groups. So here we see 3 signals. So the number of signals tells you how many unique hydrogens that you have. The next thing that we can learn from the NMR after the location and the number of signals is how big the signals are, or the intensity of the signal. And that tells us how many hydrogens are within each signal. So the idea, right, with the number of signals is how many unique hydrogens you have, but you use the intensity to say, well, how many are there total? So for example, if we go back to the example here with the 3 methyl groups coming off of 1 carbon and then the 1 methyl group coming off the oxygen, we see that there are 9 hydrogens. Now they're in green instead of the same colors that they were before, but there are 9 hydrogens in the first signal, and there's only 3 hydrogens in the second signal, in the pink signal. And so in our NMR graph, we're going to have a 3-to-1 ratio of green to pink in the height of our peaks. So the intensity is, or what we call the integral, is this blue line that looks like an S. And what we basically do is, using calculus, you can take the area under the curve of your peak and get the integration height. And so you can see that it's a 3-to-1. If you can actually measure, like even with a ruler, you can measure the height of the peaks, and you can see that the peak that's at 1.2 ppm, which is indicated by the green hydrogens, is 3 times bigger than the one that's at 3.2 by the pink hydrogens, because they're, for every 3 green hydrogens, there's 1 pink hydrogen. So there's a relative ratio of 1 to 3, with the actual ratio being, 3 pink hydrogens to 9 green hydrogens. So the size of the peak is going to tell you how many hydrogens are within that signal, how many identical hydrogens that signal is indicating. Okay, and so the last part of the NMR signal, and probably the most complicated, is going to be the splitting. So every peak that we've seen so far has just been like a single peak. But most of the time our peaks are split into our signals are split into multiple peaks. And that tells us how many neighbors each hydrogen has. So what this is called is spin-spin splitting. And the rule is going to be that basically if you have hydrogens that are not identical on a neighboring carbon to the hydrogens that you're looking at, their little unpaired magnets are going to interact with each other. And so the magnets cause splitting, and the rule is going to be here at the bottom. So it's going to be an n+1 rule. So what we do is we look for the number of neighbors, which is going to be n, and then we add 1, and then that's going to tell us our splitting. So how many splits we're going to have our signal break up into. Okay, so here's the example. So if we have this molecule here, we have HA, that's its own signal because it sees 2 bromines next to it, so it is more de-shielded farther downfield, right? It's showing up about 5.7 ppm compared to there's 2 HBs, which are only seeing 1 bromine, so they're more upfield with only seeing 1 bromine, so they're less shielded, so they're more upfield. So if we look at the spin-spin splitting, what you want to do is look at the neighboring numbers. So for example, HBs, they don't see each other because they're the same. So if we move 1 carbon away, and you're looking at neighbors or on the adjacent carbons, if we move 1 carbon away, which is the carbon that has 2 bromines and HA, we see that HBs have 1 neighbor, HA. Therefore, if we do N equals 1, because it has 1 neighbor, plus 1, we get a splitting of 2. And so you see indicated here in pink that the HB signal is split into 2 peaks. We call that a doublet. If we then look at HA, its nearest neighbors are HB, right? So it has, go one carbon away. We see the carbon that has HBs on it. There's 2 HBs. So our N for HA is equal to 2. So if we do 2 plus 1, we get 3. So HA's signal is split into 3 peaks, as shown on the left, indicated by green. And so that we call a triplet. So what you're doing with spin-spin coupling, and we'll do a lot of practice problems at the end here, is you're looking at the nearest neighbors, but are 1 carbon away, adding them up, doing that number plus 1, and that's going to tell you the splitting of the signal. And you don't include your own hydrogen in that count. So here is a table kind of indicating how this works. So you really are only caring about the columns on the left and the middle. Don't worry about the right column. So basically it tells you what your N is, and then what you're splitting your N plus 1 would be, and what we would call it. So if your N is 0, you don't have any nearest neighbors. You just have a single peak. We call that a singlet. If you have 1 nearest neighbor, just like we saw in the previous, your N plus 1 equals 2, so you have a doublet. 2 nearest neighbors, your N plus 1 is 3, triplet. 3 nearest neighbors, your N plus 1 is 4, quartet, and so on and so forth. So let's look at an example. So if we look here, we can see that we have a benzene molecule. So remember, the circle within the ring just means conjugated double bonds. So we have a benzene molecule. All the hydrogens on there are really similar. They're showing up between 7 and 8. So remember, in terms of location, I wanted you to remember that benzene shows up between 7 and 8. We see all 5 of those hydrogens. And as you can see, those hydrogens are all on top of each other, and we call that a multiplet because their signals are so, even though there would be splitting there, they're so similar that they're just on top of each other and we can't see them. The signals that we can see, however, are the CH2 and the CH3 that are indicated by the pink lines that are coming off the benzene. So if we look at their splitting, so the CH2 is closer to the benzene, so it is more downfield, which is why it's showing up about 2.6 parts per million. And if we look at the CH2, the carbon on the benzene that the CH2 is attached to has no hydrogen, so there's no neighbor there. If we go then to the right, to the CH3 that the CH2 is attached to, it has 3 neighbors, right? Because there's 3 hydrogens on the CH3. So that means its N for the CH2 is 3. And if we add 3 plus 1, we get 4. And so you can see the peak at 2.6 is split into 4. You can also see on here that it gives the integrations with the blue lines. And you can say that the integration thing telling you how many hydrogens are in that signal is showing 2 for the CH2 group in blue. So then if we do the same splitting analysis for the CH3 group, it only has it has 1 carbon neighbor, that's the CH2. So there's 2 hydrogens on there, so N is equal to 2. So we do 2 plus 1 equals 3. So we see that the peak for the CH3 group, which is the most upfield because it's the most shielded, is split into a triplet, 3 peaks, and has an integration of 3 because there's 3 hydrogens in that signal. So remember, integration has to do with the hydrogens in that signal. Splitting has to do with the neighbors to that signal. They do not indicate the same thing. So one thing to kind of keep in mind is that sometimes protons are kind of spread out and we don't see splitting. This especially happens with NHs or OHs, so amines or hydroxys or alcohols. So when you have an amine or hydroxy, a lot of the time, because they're so easy to deprotonate, right, you'll see them be really big, broad signals. So if we look at this molecule here that has an NH2, the H is showing up that's on the nitrogen, but it's kind of this blob of a peak, and we don't see any splitting or anything. And so just don't be thrown off if you don't see your NH or your OH, or if you're not seeing any splitting by neighbors or anything like that. That's just because of the nature of those groups. So it's just something to keep in mind. Okay, so what we're going to do for the rest of this video is practice problems. So what I would suggest is getting the notes, working on the practice problem yourself, and then coming back to this video to get the answers to the practice problems that are going to work through how do we take NMR and then at the end, NMR and IR and figure out the structure? So, for example, we look at this first one. So it says propose a structure for the compound of the molecular formula C4H10, whose proton NMR spectrum is as follows. So there's a way to approach this. The first thing to do, if you're only given NMR and the molecular formula, the first thing to do is calculate the DU. So what we did in the very beginning of the semester to calculate the degree of unsaturation, because that will tell you if you have any double bonds or anything like that, and it gives you a starting point for drawing this structure. So if we look at the solved problem here, the first thing we're going to do is calculate the DU. So again, I calculate the DU using the formula below at the bottom of the screen, and I find that my DU is 0. And then, so that tells me I don't have any double bonds or rings or anything like that. And then what I want to go on to do is look at the rest of the proton NMR to figure out my structure. And so the way that I suggest that you do this in the way is that you look at the number of signals you have, you look at their splitting and try to draw the molecule from that, and then check your molecule that you've drawn to see if it matches what the spectra is. You're not going to be able to just kind of magically come up with the correct molecule right from the start. It's going to be kind of a guess and check. So I can rationalize the molecule that is the correct product by looking at the NMR, and I see, okay, I have 4 unique hydrogens, and I have that in my product. I have HA, HB, HC, and an OH. Remember, OHs are special, so they don't split or anything like that. And so that's why I've labeled the OH as the singlet that comes around 2.5. And then I have splitting, if I look just kind of as from most de-shielded to most shielded, I look at HC, it's the farthest downfield. And so those are the ones that are closest to the OH. And if I look at the splitting of HC, it has one nearest neighbor, HA. That's not, again, we're not counting the OH here. And so since it has one nearest neighbor, it is a doublet in its signal. If I then move out to look at HA, I have HA is the next most downfield. So it's the one that's showing up about 1.8. And it has 8 nearest neighbors because it has 6 HB neighbors and 2 HC neighbors. So a total of 8, which gives it a splitting of 9. Because remember, for nearest neighbors, it's any hydrogen 1 carbon away. And so that makes sense. And then if I look at HBs, they are my most upfield because they are farthest away from the oxygen. And HBs have 1 neighbor, HA, so they are a doublet. Going for the next example, we're going to treat it the same way as before. So work on this on your own and then switch to the answers. So if we look here, we're going to see that we have DU of 4 because of our C9H12 molecular formula. And 4 DU means that you have a lot of degrees of unsaturation. And if I look at my NMR, I see that I have a peak around 7. And remember, the one peak that I wanted you to remember that shows up around 7 is going to be a benzene. And a benzene has a DU of 4 because it has 3 double bonds and a ring. So that's a total of 4 DU. So all my DU is taken up in the benzene. And I can see that the benzene has 5 hydrogens, the number 5H, that's at the top, that's the integration. And that tells me that the benzene only has 1 carbon that doesn't have a hydrogen on it, which is how I drew my molecule down at the bottom. The other 2 signals I have, which are shown at about 3 and about 1 or 1.2-ish. So I have 2 other signals, and these are similar to the ones that we saw in the first example, or in the previous example, where I have 1 hydrogen that's seeing a lot of neighbors and 6 hydrogens that are seeing 1 neighbor because they're a doublet. And so that gives me this isopropyl group again. The big thing to remember is to not look at the peak that is at 0 or not count it in your signal counting because the peak at 0 is that TMS reference. This next example is showing you the power of symmetry in simplifying an NMR spectrum. So you can see that we have a molecular formula that has a bunch of atoms, C5H10, with a DU of 0, but we only have 1 signal in the NMR, and it's not split at all. It's a singlet, which means that, in theory, the hydrogens have no nearest neighbors that are different from them. And so the way that this molecule works is that we actually have a cyclopentane. And the reason that all of the hydrogens on the cyclopentane are identical is because there is symmetry throughout the molecule. And so every hydrogen is seeing itself, so we have no splitting. And since they're all the same, they all show up under 1 signal. So the last two examples are going to be how we can couple NMR with IR to figure out a structure. So remember, IR just tells us functional groups, whereas NMR allows us to actually put the molecule together in total. So if we look at this example here, from the IR, we can know two things. We see that we have only sp3CHs because of that signal that's just below 3000. And then we see that we have a carbonyl of some sort. We don't know whether it's a ketone, an aldehyde, an ester, because we do have a second oxygen, or but it's not a carboxylic acid because we don't have that OH peak in the IR. But we don't know what of the other three that carbonyl is, so we have to look at the NMR to get that information. So as with before, we want to just calculate the DU, and we see that we have a DU of 1. So that tells us our double bond in the carbonyl is what is the only double bond that we have. And so then if I know that I have a carbonyl, and then I need to figure out everything else. And what I found is that I actually have this ester compound, because if I look at the hydrogen signals, I have 3 unique hydrogen signals, again, ignoring the peak at 0. And of those hydrogen signals, 3 of them, H, that are just below 4, have no nearest neighbors. And then the other 2 sets are 2 hydrogens that see 3 nearest neighbors and 3 hydrogens that see 2 nearest neighbors, because the 2 hydrogens are a quartet and the 3 hydrogens are a triplet. And so that tells me that in my singlet 3 hydrogens, the ones just below 4, not only do they see no nearest neighbors, but they're also the most downfield. So I can rationalize the structure that I drew, having HA being all by itself and connecting to an oxygen, making it the most downfield. Then comes HB, which is on the other side of the carbonyl. HB sees 3 nearest neighbors, HC, which makes it a quartet. And it's the second most downfield because it's right next to the carbonyl. And then HC by themselves are seeing just HBs, so that makes them a triplet. And they're the farthest upfield because they're the farthest away from the ester group. And so here you can start to see a pattern that anytime you have an ethyl group, HB, that are shown like with HBs and HCs, they always have this pattern of having a quartet and then a triplet, because it's 2 hydrogens seeing 3 and 3 hydrogens seeing 2. Okay, so this last example, example 4, again, we're going to have both IR and NMR, and we're going to figure out the structure. So if we look at the IR here, we have kind of similar to our IR last time. We have sp3CHs just below 3000, and then we have a carbonyl peak that, again, we don't know what type of carbonyl, we just know it's a carbonyl. So if we do the DU of C5H9BrO2, we see that we get a DU of 1, and so that's going to be our carbonyl. And we find after analyzing that we actually have an ester again, which it gives us the signals that we have in the hydrogens. So if I just looked at the NMR, not knowing what the compound is, I see that I have 4 unique hydrogen signals, and it's a CH2 group. It's 3 CH2 groups, the ones that are the most downfield, the one just below or just above 4, just below 4, and around 3. And then I have a CH3 group saying 3 hydrogens that is about 1.5. So if I look at my molecule that I've drawn, I can rationalize the splitting and the shifts of the product or of the molecule that's drawn to match the NMR. So I have an ethyl group in HB and HA, and that's what's shown in HA being the farthest upfield because it's the farthest away from the oxygens and the bromide. And it sees 2 neighbors, so it's split into a triplet. And then HB being the farthest downfield because it sees, that's the one that sees 3 neighbors, and so it's a quartet. So I can tell that HB is the one that's furthest downfield because that's the only one that's a quartet and sees 3 neighbors. I then have HC and HD that are both split into triplets because they both see each other, so they see 2 neighbors each, with HG being more downfield, than HC because it is next to the bromine. Whereas HC, although it's next to the carbonyl, bromine is more electron withdrawing, so it's farther downfield.